Hello and welcome to the Midnight Lab. Before we begin, take a moment to like the video and subscribe to the channel if you enjoy calm science and relaxing explorations of the natural world. And if you feel like sharing, let me know where you're watching or listening from tonight. It's always fascinating to see where everyone is tuning in from, because wherever you are on Earth right now, the atmosphere above you is doing something quietly remarkable. Perhaps outside your window the air is completely still. Perhaps there's rain tapping softly on the roof. Or maybe the wind is moving through trees somewhere nearby. Whatever the weather is doing where you are, it's part of a vast invisible system constantly in motion above our planet. Weather can often feel random, unpredictable, almost mysterious. One day the sky's perfectly clear, and the next clouds roll in and the wind begins to rise. Storms form seemingly out of nowhere. Rain appears, disappears, and returns again. And for most of human history, weather felt like something almost magical, something that simply happened. But the truth is something far more fascinating. Weather is not random at all. Every breeze, every cloud, every storm, every drop of rain is the result of an immense planetary engine powered by energy from the sun, shaped by the rotation of the Earth and guided by the subtle physics of air, water, and heat moving through the atmosphere. Right now, high above us, rivers of wind are flowing around the planet at hundreds of miles per hour. Vast waves of air are slowly undulating across continents. Oceans are quietly releasing heat into the sky. Tiny microscopic particles are helping clouds form droplet by droplet. And all of it together produces the weather we experience every single day. Tonight, we're going to take a slow and gentle journey through that invisible system. We'll explore how sunlight powers the atmosphere, how air begins to move, how clouds appear, how storms grow, and how scientists have gradually learned to understand the hidden physics shaping the skies above us. Along the way, we'll meet the curious thinkers who helped uncover these patterns, from early scientists watching the sky with simple instruments, to modern researchers using satellites and supercomputers to simulate the entire atmosphere. But we'll take it slowly. There's no rush. Because the atmosphere itself moves in rhythms that are often surprisingly calm, broad, sweeping motions that unfold over hours, days, and sometimes even weeks. So wherever you are right now, whether you're listening in the quiet of the evening, settling in for a sleep, or simply curious about the science of the skies, take a moment to relax. Maybe glance out the window if you can. Above you, the atmosphere is already at work, quietly shaping the weather that will arrive tomorrow. And tonight, we're going to explore how weather actually works. If you could somehow rise gently upward from where you are right now, drifting higher and higher into the sky, the first thing you might notice is how thin the air really is. The atmosphere that surrounds our entire planet looks enormous from the ground, yet compared with the size of Earth itself, it is surprisingly delicate. If our planet were the size of a large apple, the atmosphere would be roughly as thin as the apple's skin, and yet inside that thin layer exists one of the most intricate natural systems on Earth. The atmosphere is not simply a blanket of air sitting quietly above us. It is constantly moving, constantly exchanging energy, constantly reorganizing itself. Air rises and sinks, water evaporates and condenses. Heat spreads outward from warmer regions toward cooler ones. Vast rivers of wind sweep across continents, while towering clouds form and dissolve hour by hour. To scientists, this behavior reveals something remarkable. The atmosphere is what is known as a complex system. A complex system is a system made up of many interacting parts whose collective behavior cannot be understood simply by examining each piece individually. Instead, patterns emerge from the interactions themselves. Flocks of birds swirling through the sky, schools of fish turning in perfect synchrony, and the traffic patterns of large cities all fall into this category. Weather belongs in that same family. At the most basic level, the atmosphere is composed of molecules of gas, mostly nitrogen and oxygen, along with smaller amounts of water vapour, carbon dioxide, and other trace gases. Each individual molecule moves randomly, colliding with its neighbours billions of times every second. On their own, these tiny collisions appear chaotic and unpredictable, but when trillions upon trillions of those interactions occur together, something extraordinary happens. Large-scale patterns begin to form. Winds organise into global circulation systems. Storms grow into spiralling structures visible from space. Bands of clouds stretch across entire oceans. Out of microscopic randomness, enormous order emerges. One of the scientists who helped explain this kind of behaviour was the Russian-born Belgian physical chemist Ilya Prigogine. In the 1970s, he developed the theory of what he called dissipative structures. His work explored how organised patterns can arise in systems that are far from equilibrium. In simple terms, a system in equilibrium is calm and balanced. Nothing much changes, but when energy flows through a system continuously, the system can reorganize itself into stable patterns that help move that energy along. A classic example is a pot of water heating on a stove. When the water first warms, the motion of molecules is random. But as more heat enters the system, the water suddenly begins to form organized convection cells. Rising columns of warm water and sinking columns of cooler water appear spontaneously. Prigogine realized that similar self-organizing behavior occurs throughout nature, and the atmosphere above our heads is one of the most striking examples. Energy from the sun constantly pours into Earth's atmosphere. That energy never spreads evenly. The equator receives far more sunlight than the poles. Oceans absorb heat and release it slowly. Ice reflects sunlight back into space. Land warms and cools quickly. Clouds scatter and trap radiation in complex ways. The result is a system that is permanently out of balance, and that imbalance is exactly what keeps the atmosphere moving. Weather, in essence, is the atmosphere's ongoing attempt to redistribute energy. Warm air rises, cold air sinks, winds form as the atmosphere tries to smooth out differences in temperature and pressure. Clouds form when moist air cools and water vapor condenses. Storms grow when energy stored in warm, moist air is suddenly released. All of these processes are different expressions of the same underlying principle: energy moving through a fluid system that is constantly reorganizing itself. But the atmosphere does not operate alone. It is one part of a much larger planetary system. Earth scientists often describe our planet using the idea of the Earth system. This concept recognizes that the atmosphere interacts continuously with the oceans, the land surface, the frozen regions of ice, and even the living organisms that inhabit the planet. The oceans, for example, store enormous quantities of heat. Water absorbs solar energy during warm periods and releases it gradually back into the atmosphere. This exchange helps regulate global temperatures and influences weather patterns across entire continents. Land surfaces also play their role. Dark forests absorb sunlight differently than bright deserts. Mountain ranges redirect winds and force air to rise, creating clouds and rainfall. Even the moisture released by plants during transpiration contributes water vapor to the air. The biosphere, meaning the living component of Earth, also influences the atmosphere in subtle ways. Forests release organic particles that help clouds form. Marine plankton produce compounds that affect atmospheric chemistry. Over long time scales, life has even altered the composition of the atmosphere itself. The air we breathe today contains about 21% oxygen, largely because ancient photosynthetic organisms gradually released oxygen into the atmosphere over hundreds of millions of years. So when we talk about weather, we're really talking about the behavior of an interconnected planetary system. One of the scientists who helped reveal how large-scale patterns emerge within this system was Carl Gustav Rossby. Born in the late 1800s and working primarily during the early 20th century, Rossby became one of the founding figures of modern atmospheric science. Rossby studied how the rotation of Earth influences the movement of air across the planet. As Earth spins, moving air masses are deflected in ways that create enormous wave, like patterns in the upper atmosphere. Today these patterns are known as Rossby waves. Rossby waves can stretch for thousands of miles across the globe. They shape the path of the jet stream, guide storm systems across continents, and influence the long-term patterns of weather we experience at the surface. Seen from space, these waves can sometimes appear as vast, undulating rivers of air winding across the planet. They are one of the reasons weather systems often travel from west to east across many regions of the world. Rossby's work helped scientists understand that the atmosphere is not just swirling randomly, it follows physical laws that govern the motion of fluids on a rotating sphere. At the same time, other scientists were beginning to think about Earth as a self-regulating system. In the 1970s, British scientist James Lovelock proposed an idea that would become widely known as the Gaia hypothesis. Working alongside microbiologist Lynn Margulis, Lovelock suggested that life and the environment might interact in ways that help maintain conditions favourable for life on Earth. The Gaia hypothesis does not claim that Earth is literally alive. Instead, it proposes that biological processes can influence atmospheric and environmental conditions in ways that create long-term stability. For example, plants absorb carbon dioxide during photosynthesis and release oxygen. Marine microorganisms affect cloud formation. Forests alter humidity and rainfall patterns. Over geological timescales, these processes can influence the composition of the atmosphere and the balance of gases that regulate planetary temperature. Although the Gaia hypothesis has been debated and refined over the years, it helped encourage scientists to think about Earth as a system of interacting components rather than isolated pieces. And when we look at weather through that lens, a powerful picture begins to emerge. Weather is not simply wind or rain or clouds appearing from nowhere. It is the visible expression of energy moving through a rotating planetary fluid. The atmosphere behaves much like a vast ocean of air, flowing around the planet under the influence of gravity, solar heating, and Earth's rotation. Differences in temperature create differences in pressure. Differences in pressure drive winds. Winds transport heat and moisture. Moisture forms clouds and storms. Storms release energy and reshape the flow of air. The entire system is in constant motion. Even when the sky appears calm, invisible processes are unfolding overhead. Warm air may be rising slowly somewhere beyond the horizon. A river of wind may be flowing high above the clouds. Moisture from distant oceans may be drifting quietly toward land. All of these movements are connected, and together they form one of the most complex and fascinating natural systems on our planet. a delicate layer of air only a few miles thick compared with the size of Earth, yet capable of producing towering thunderstorms, sweeping winds, and global patterns that stretch across hemispheres. The atmosphere may appear gentle when we look up at a peaceful sky, but behind that calm surface lies a vast planetary engine quietly redistributing energy around the world. If weather is the movement of energy through the atmosphere, then the obvious question is where that energy comes from in the first place. The answer, of course, lies 93 million miles away. Every second, the sun pours an enormous amount of energy into space in the form of electromagnetic radiation. Only a tiny fraction of that energy reaches Earth, yet even that small portion is enough to power nearly every atmospheric process we experience. Sunlight travels across the emptiness of space and arrives at Earth as a steady stream of radiation. Some of that radiation is visible light, the portion our eyes can see. Some arrives as infrared energy, which we experience as warmth. Other parts of the spectrum include ultraviolet radiation and several additional forms of electromagnetic energy. When this sunlight reaches Earth, it does not spread evenly across the planet. Because Earth is spherical, sunlight strikes the equatorial regions more directly. Near the equator, the sun's rays arrive at a steep angle, concentrating energy over a relatively small surface area. Near the poles, the sunlight arrives at a shallow angle, spreading the same amount of energy across a much larger region. This simple geometric difference has enormous consequences. Regions near the equator receive far more solar energy than regions near the poles. On average, the tropics gain more heat than they lose to space. The polar regions, by contrast, lose more heat than they receive. This imbalance sets the entire atmosphere into motion. But before that energy can move through the atmosphere, something important happens at Earth's surface. Sunlight interacts with the ground, the oceans, the ice, and the clouds in different ways. Some surfaces absorb solar radiation efficiently, converting light into heat. Others reflect a large fraction of incoming sunlight back into space. The fraction of incoming sunlight that a surface reflects is known as albedo. Fresh snow has an extremely high albedo, reflecting roughly 80 to 90% of the sunlight that strikes it. Dark ocean water reflects far less, often absorbing most of the incoming radiation. Forests, deserts, grasslands, and cities each have their own characteristic albedo. Clouds also play a powerful role in this balance. Bright, thick clouds can reflect significant amounts of sunlight back into space before it ever reaches the ground. At the same time, clouds can trap heat rising from Earth's surface, acting somewhat like an insulating blanket. The combined effect of all these reflective and absorptive processes determines how much solar energy the planet ultimately retains. Planetary albedo is the term scientists use to describe the overall reflectivity of the entire Earth. On average, about 30% of incoming solar radiation is reflected back into space by clouds, atmospheric particles, ice, and reflective surfaces. The remaining 70% is absorbed by the atmosphere, the land, and the oceans. Once absorbed, that energy begins to warm the planet, yet Earth cannot simply continue warming indefinitely. For a planet to remain stable over long periods of time, the energy it absorbs must eventually be balanced by the energy it sends back into space. This balance between incoming solar radiation and outgoing planetary radiation is known as radiative equilibrium. The basic principle can be expressed very simply. Energy absorbed by Earth must equal energy emitted back into space. When that balance is achieved, the planet's average temperature remains relatively stable. But the atmosphere complicates this balance in fascinating ways. Earth does not radiate energy back into space as visible sunlight. Instead, the planet emits infrared radiation, a form of heat energy produced as the surface warms. Some of this outgoing infrared radiation escapes directly into space. However, certain gases in the atmosphere absorb portions of this radiation and re-emit it in multiple directions. These gases include water vapor, carbon dioxide, methane, and several others known collectively as greenhouse gases. The result is that some of the heat leaving Earth's surface is redirected back toward the ground, slightly warming the lower atmosphere and surface compared with what would occur if the atmosphere were perfectly transparent to infrared radiation. Understanding this delicate balance between incoming solar radiation and outgoing heat became one of the central challenges of climate science. One of the earliest scientists to explore this problem in detail was the Swedish chemist Svante Arrhenius. In the late 1800s, Arrhenius began calculating how changes in atmospheric gases might influence Earth's temperature. Using basic physical principles and painstaking manual calculations, he estimated how carbon dioxide could affect the planet's ability to retain heat. His work represented one of the first attempts to quantify the relationship between atmospheric composition and global temperature. Although his calculations were simple compared with modern climate models, the underlying concept was remarkably insightful. Arrhenius understood that the atmosphere does not simply sit passively above the planet. It actively participates in controlling how energy flows through the Earth system. Another key principle underlying these ideas is known as Kirchhoff's law of thermal radiation. This law, developed by German physicist Gustav Kirchhoff in the 19th century, describes the relationship between how objects absorb radiation and how they emit it. In essence, Kirchhoff demonstrated that a good absorber of radiation is also a good emitter of radiation. In the context of Earth's climate system, this principle helps explain how the atmosphere interacts with heat energy. Gases that absorb infrared radiation also emit infrared radiation. This constant exchange of absorption and emission creates a complex energy balance within the atmosphere. The atmosphere is therefore not simply a barrier between Earth and space. It behaves more like an active participant in the planet's thermal system, absorbing, emitting, and redistributing energy in every direction. And yet, even with all these interactions, the fundamental imbalance between equator and poles remains. The tropics receive far more solar energy than they can radiate away locally. The polar regions lose more energy than they receive. If energy could not move across the planet, the equator would grow steadily hotter, while the poles would grow progressively colder. But the atmosphere and the oceans work together to prevent this extreme outcome. Winds transport warm air away from equatorial regions toward higher latitudes. Ocean currents carry heat through massive circulating flows of water. Storm systems mix warm and cold air masses together. All of these processes exist for a single underlying reason. They help redistribute energy across the planet. At any given moment, the equatorial regions of Earth are receiving roughly 2.5 times more solar energy per square meter than the polar regions during winter months. Without atmospheric circulation, these differences would lead to temperature contrasts far greater than anything we currently experience. Instead, the atmosphere continuously works to smooth out these imbalances. Air warmed near the equator begins to rise, expanding as it climbs upward into lower pressure. As that air rises, cooler air flows in to replace it. The resulting movement creates enormous circulation patterns that stretch thousands of miles across the globe. Some of this energy is carried northward and southward by the winds high in the atmosphere. Some travels through ocean currents slowly circulating through the depths of the sea. Some is released in towering thunderstorms that carry heat upward into the upper atmosphere. The atmosphere is therefore not simply reacting to sunlight, it is constantly responding to uneven heating. Weather systems form, move, and evolve largely because the planet is trying to redistribute solar energy from places where it is abundant to places where it is scarce. And in that quiet effort to balance energy across a rotating sphere, the familiar patterns of weather begin to emerge. Warm tropical air rising toward the sky, cold polar air drifting toward lower latitudes, storms spinning across oceans, clouds gathering where rising air cools and moisture condenses. All of these processes trace their origins back to the same fundamental source. A star shining 93 million miles away, continuously sending energy across space. And the thin, restless atmosphere of Earth, endlessly working to move that energy around the world. If you could continue drifting upward through the sky, rising slowly through the atmosphere, you would begin to notice that the air around you changes in surprisingly structured ways. The atmosphere is not a single uniform layer. Instead, it is arranged into several distinct regions stacked one above another, each defined by how temperature changes with altitude. The lowest of these layers is the troposphere. The troposphere is where almost all weather takes place. It stretches from Earth's surface up to an altitude of roughly 6 to 10 miles depending on location. Near the equator it extends a little higher, while near the poles it becomes somewhat thinner. Within this relatively shallow layer exist the familiar features of everyday weather. Clouds form here. Rain falls here. Thunderstorms rise upward through this region like enormous columns of boiling air. The reason weather occurs primarily in the troposphere is fairly straightforward. Most of the atmosphere's water vapor is concentrated close to the surface. Water vapor is the fuel for clouds, precipitation, and storms. Without it, weather as we know it would be impossible. In addition, the troposphere is where most of the atmosphere's mass resides. Nearly 80% of the total mass of the atmosphere lies within this lowest layer. With so much air compressed near the surface, there is plenty of material for winds, pressure systems, and storms to work with. But perhaps the most important feature of the troposphere is how temperature changes as you move upward. In this region, air generally becomes colder with increasing altitude. On average, temperature decreases by roughly 6.5 degrees Celsius for every kilometre of height gained. This gradual cooling with altitude plays a crucial role in determining how air behaves. Warm air tends to rise, cold air tends to sink. This simple rule, driven by differences in density, lies at the heart of atmospheric motion. When air near the ground becomes warmer than the air above it, the warmer air becomes less dense and begins to rise. As it rises, cooler air moves in to replace it. The resulting motion creates upward currents known as convection. Convection is responsible for many familiar weather features. It drives the towering clouds of thunderstorms. It lifts warm air upward where it cools and forms cloud droplets. It helps mix the lower atmosphere, spreading heat and moisture around. Above the troposphere lies the stratosphere, a very different environment. In the stratosphere, temperatures begin to increase with altitude rather than decrease. This warming occurs largely because of ozone, a form of oxygen that absorbs ultraviolet radiation from the sun. As ozone absorbs this radiation, it heats the surrounding air. The increase in temperature with height makes the stratosphere very stable. Air in this layer resists vertical motion, which is why large weather systems rarely extend into it. Even higher lie the mesosphere and thermosphere, regions where temperatures and densities behave in increasingly unusual ways as the atmosphere gradually fades into the vacuum of space. Yet for the purposes of everyday weather, the troposphere remains the main stage where atmospheric activity unfolds. Within this layer, meteorologists often focus on a concept known as atmospheric stability. Atmospheric stability describes whether a parcel of air, if pushed upward or downward, will continue moving in that direction or return to its original position. Imagine a small bubble of air near the surface that becomes slightly warmer than its surroundings. If that air parcel begins to rise and finds itself still warmer than the air around it, it will continue rising. The atmosphere in this case is unstable. If the rising parcel quickly becomes cooler than the surrounding air, it will sink back toward its starting point. In that situation, the atmosphere is considered stable. To analyze this behavior, meteorologists often use a concept known as potential temperature. Potential temperature is the temperature that a parcel of air would have if it were moved to a standard reference pressure without gaining or losing heat. In simpler terms, it allows scientists to compare air parcels that exist at different pressures and altitudes in a consistent way. This concept is useful because pressure decreases as altitude increases. When air rises, it expands and cools even if no heat leaves the parcel. Potential temperature accounts for that expansion, allowing meteorologists to determine whether air is truly gaining or losing heat, compared with its surroundings. When potential temperature increases with altitude, the atmosphere is generally stable. When it decreases with altitude, the atmosphere becomes unstable and prone to convection. Understanding these vertical temperature patterns is essential for predicting weather. One of the earlier scientists to attempt large-scale weather prediction using physical equations was the British mathematician and meteorologist Lewis Fry Richardson. In the early 1900s, Richardson envisioned forecasting weather by solving the equations that describe atmospheric motion. These equations include relationships between pressure, temperature, wind speed, and air density. Today, powerful computers solve millions of these calculations every second. But Richardson lived long before the age of modern computing. Undeterred, he attempted to perform the calculations by hand. In 1922, Richardson published a book titled Weather Prediction by Numerical Process. In it, he described an ambitious plan for forecasting weather using mathematical equations. His method required enormous numbers of calculations. Richardson imagined a vast hall filled with thousands of people working together like human computers, each solving a small portion of the equations and passing results along to the next person. While the idea may sound unusual today, the principle behind it turned out to be remarkably forward-thinking. Modern weather forecasting models operate using exactly this approach, except the calculations are now performed by supercomputers rather than rooms full of mathematicians. Richardson's work also highlighted how sensitive atmospheric motion is to small changes in temperature and pressure. One of the mechanisms responsible for generating large weather systems from these small differences is known as baroclinic instability. Baroclinic instability occurs when strong temperature differences exist across a region, especially along boundaries between warm and cold air masses. In mid-latitude regions, such as much of North America, Europe, and Asia, warm tropical air frequently meets colder polar air. Along the boundary where these air masses interact, temperature gradients can become quite sharp. When air flows along such a boundary, small disturbances can begin to grow. Because warm air is less dense than cold air, the atmosphere begins to rearrange itself in ways that convert stored temperature differences into motion. Waves form along the boundary. These waves can amplify, eventually developing into the large rotating storm systems known as extratropical cyclones. These storms are the familiar weather systems that bring rain, snow, and changing winds across many parts of the world. Baroclinic instability therefore represents one of the key engines that drives mid-latitude weather. It transforms the energy stored in horizontal temperature differences into moving storms and swirling winds, and once again the underlying cause can be traced back to the same principle we encountered earlier. Uneven heating across the planet creates differences in temperature. Differences in temperature create differences in density. Differences in density drive the movement of air. That movement organizes itself into storms, winds, and clouds, and all of it unfolds within a relatively thin layer of air wrapped around our planet, where rising warm air and sinking cold air continuously reshape the atmosphere above us. To understand why air moves through the atmosphere, it helps to begin with a simple realization. Air is a fluid. We often think of fluids as liquids like water flowing through rivers or filling the oceans, yet gases behave in remarkably similar ways. Air can flow, swirl, accelerate, and form waves just like water. The difference is that air is far less dense and far more invisible, which makes its movements harder to notice directly. Despite that invisibility, the motion of air follows the same physical laws that govern the motion of any other fluid. These laws are described by a set of mathematical relationships known as the Navier-Stokes equations, named after the 19th century physicists Claude-Louis Navier and George Gabriel Stokes. These equations describe how fluids move under the influence of forces such as pressure, viscosity, gravity, and external energy inputs. At their heart, the Navier-Stokes equations describe the conservation of momentum in a fluid. They account for how a parcel of fluid accelerates when forces act upon it, how internal friction slows motion, and how pressure differences create flow. If written in plain language, this central idea can be summarized in a simple way. The change in motion of a fluid equals the sum of forces acting on that fluid. In other words, whenever air speeds up, slows down, or changes direction, it must be responding to forces acting upon it. The atmosphere is therefore constantly responding to a balance of forces that push, pull, and redirect the motion of air. Among these forces, one stands above the rest as the primary driver of wind. This force is known as the pressure gradient force. Air pressure is simply the weight of the atmosphere pressing down on the surface of Earth. Every column of air above us has mass, and gravity pulls that mass toward the ground. The combined weight of all that air creates atmospheric pressure. At sea level, the average atmospheric pressure is roughly 100,000 pascals, which corresponds to about 14 pounds of force, pressing on every square inch of surface area. Fortunately, our bodies are adapted to this pressure, so we do not feel it directly. However, atmospheric pressure does not remain perfectly uniform across the planet. When air warms, it expands and becomes less dense. When air cools, it contracts and becomes denser. These differences in density cause pressure variations across regions of the atmosphere. Where air accumulates, pressure becomes higher. Where air rises and spreads outward, pressure becomes lower. Nature tends to resist these imbalances. Whenever a region of higher pressure sits beside a region of lower pressure, The atmosphere responds by moving air from the higher pressure area toward the lower pressure area. This movement is the pressure gradient force. The strength of this force depends on how quickly pressure changes across distance. When pressure differences are small and spread out over large areas, the resulting winds tend to be gentle. When pressure differences are sharp and concentrated, winds can become quite strong. If you have ever watched weather maps showing tightly packed lines around a storm system, those lines represent regions where pressure changes rapidly across short distances. Meteorologists call these lines isobars, and closely spaced isobars usually indicate strong winds. But recognizing that pressure differences create wind was only one part of the scientific puzzle. In the late 19th century, a Norwegian physicist named Wilhelm Bjerknes proposed a revolutionary way of thinking about weather. Bjerknes suggested that weather forecasting should not rely solely on observation and experience. Instead, he argued that weather could be predicted by applying the fundamental laws of physics to the atmosphere. In a lecture delivered in 1904, Bjerknes outlined a bold idea. If scientists could measure the state of the atmosphere accurately and apply the equations governing fluid motion and thermodynamics, it should be possible to calculate how the atmosphere would evolve over time. His proposal essentially framed weather prediction as a problem in physics. The atmosphere, according to Bjerknes, behaved like a vast physical system governed by measurable forces. If those forces could be quantified and the equations solved, the future state of the atmosphere could be predicted. This idea laid the foundation for modern numerical weather forecasting. Today, massive computer models analyze millions of atmospheric measurements collected from satellites, weather stations, aircraft, and weather balloons. These models apply physical equations derived from the Navier-Stokes framework to simulate how air will move and how weather systems will evolve. Although these models are extraordinarily complex, the core idea remains the same one Bjerknes described more than a century ago. Weather is physics in motion. Another important concept in atmospheric motion is something called vorticity. Vorticity describes the tendency of a fluid to rotate. If you stir a cup of tea with a spoon, the swirling motion that appears in the liquid is an example of vorticity. The fluid begins to spin around a central point. Air can behave in much the same way. In the atmosphere, rotating motion appears on many different scales. Tiny whirlwinds may spin briefly along the ground on hot summer days. Thunderstorms may develop rotating updrafts known as mesocyclones. On much larger scales, hurricanes and mid-latitude cyclones form enormous rotating systems hundreds of miles across. Even the large-scale circulation of the atmosphere contains rotating patterns that extend across entire continents. Vorticity helps meteorologists understand how these rotating motions develop and evolve. Some of this rotation originates from the Earth itself. Because our planet rotates, moving air masses tend to curve as they travel across the surface. This effect will become even clearer when we examine planetary rotation more closely. But rotation can also arise from the way air flows around pressure systems and temperature boundaries. For example, when air flows toward a region of low pressure, the inward motion often begins to twist into a spiral. As air converges and rises, the conservation of angular momentum can cause the rotation to intensify, much like a spinning ice skater pulling in their arms to spin faster. This is one reason why large storm systems often develop characteristic spiral structures. Within these rotating systems, air is constantly being drawn inward, lifted upward, and spread outward again at higher altitudes. Once again, the underlying driver remains pressure differences. Air flows from high pressure toward a low pressure. As it moves, it interacts with Earth's rotation, temperature gradients, and friction near the surface. These interactions create complex patterns of motion that we experience as wind. Sometimes the motion is gentle, like a soft evening breeze. Sometimes the motion becomes dramatic, producing powerful storms capable of transporting enormous amounts of energy through the atmosphere. Yet behind all of these different experiences lies a remarkably consistent principle. Differences in pressure create forces. Forces accelerate air. Moving air carries heat, moisture, and momentum across the planet. And through this continual motion, the atmosphere redistributes energy across Earth's surface, maintaining the delicate balance that keeps our planet's climate system in motion. In that sense, every gust of wind we feel is the visible expression of invisible forces constantly shaping the atmosphere above us. If Earth did not rotate, the movement of air across the planet would be far simpler. Warm air rising near the equator would drift directly toward the poles. Cold air would slide back toward the equator along the surface. Winds would travel mostly in straight lines from high pressure toward low pressure, creating a fairly simple pattern of atmospheric circulation. But Earth does rotate. Our planet completes one full rotation every 24 hours, spinning steadily from west to east. At the equator, the surface of Earth moves through space at a speed of roughly 1,000 miles per hour due to that rotation. Even locations far from the equator are still moving quickly as the planet turns beneath the atmosphere. This rotation has a profound influence on the motion of air. When air begins to move across Earth's surface, it does not simply travel in a straight path. Instead, its motion is subtly curved by the rotation of the planet itself. This apparent deflection of moving objects in a rotating system is known as the Coriolis effect. The Coriolis effect was first described mathematically in the 19th century by the French mathematician and engineer Gaspard Gustave Coriolis. Coriolis was studying the motion of objects within rotating mechanical systems when he realized that rotating frames of reference introduce additional forces that appear to deflect moving objects. When applied to Earth's atmosphere, the Coriolis effect causes moving air to bend toward the right in the northern hemisphere and toward the left in the southern hemisphere. This deflection does not arise because air physically pushes itself sideways. Instead, it occurs because different parts of Earth's surface are moving at different speeds as the planet rotates. Near the equator, the surface moves faster because it must travel a larger circle during each rotation. Near the poles, the surface moves more slowly because the circle of rotation becomes much smaller. When air begins moving northward or southward across these regions, it carries with it the rotational speed it had at its starting point. As the air travels into regions where the surface is moving faster or slower, its motion appears to curve relative to the ground below. The effect is subtle for small motions, but over large distances it becomes extremely important. Without the Coriolis effect, winds would flow directly from high-pressure areas to low-pressure areas in straight lines. With the Coriolis effect, those winds curve, forming spirals and waves that give the atmosphere its complex patterns. Meteorologists often measure the importance of this rotational influence using a quantity known as the Rossby number. The Rossby number is named after Carl Gustav Rossby, one of the pioneering figures in modern atmospheric science. Rossby spent much of his career studying how Earth's rotation shapes large-scale atmospheric motion. The Rossby number compares two influences on moving air. One influence comes from the natural inertia of the air itself, which tends to keep it moving in a straight line. The other influence comes from the rotational effects of the planet. In simple terms, the Rossby number tells scientists whether rotation is important for a particular atmospheric motion. When the Rossby number is large, inertia dominates, and the Coriolis effect is relatively weak. This situation often occurs in small-scale motions such as gusts of wind near the ground or localized thunderstorms. When the Rossby number is small, rotational forces dominate. This is typical for large-scale atmospheric flows that extend across hundreds or thousands of miles. For these large systems, the rotation of Earth strongly influences how air moves. One of the reasons large storm systems develop rotating structures lies in a principle known as conservation of angular momentum. Angular momentum describes the tendency of rotating systems to preserve their rotational motion unless acted upon by an external force. A familiar example occurs when a figure skater spins on ice. When the skater pulls their arms inward, their rotation speeds up. When the skater extends their arms outward, the rotation slows. The total angular momentum of the system remains the same, but the distribution of mass changes the rotation speed. Something similar can happen within the atmosphere. When air flows inward toward a region of low pressure, it often begins to spiral. As the air moves closer to the center of the system, the radius of its circular motion becomes smaller. Because angular momentum must be conserved, the rotation tends to intensify. This is one reason why powerful storm systems such as hurricanes develop strong rotating winds near their centers. The air spiraling inward toward the storm's core accelerates as the radius of rotation decreases, much like water spinning faster as it drains from a bathtub. Another concept closely related to these ideas is potential vorticity. Potential vorticity is one of the most important principles in atmospheric science, although the name itself may sound a little intimidating at first. Vorticity, as mentioned earlier, refers to the tendency of air to rotate. Potential vorticity combines that rotational tendency with the vertical structure of the atmosphere and the conservation of certain physical properties. In essence, potential vorticity describes how the spin of an air parcel changes when the parcel moves through regions of different thickness in the atmosphere. If an air column becomes stretched vertically, its rotation can intensify. If the column becomes compressed, the rotation can weaken. This behavior follows a principle similar to the conservation of angular momentum. Meteorologists rely heavily on potential vorticity because it helps track how air masses move, how storms evolve, and how atmospheric waves propagate across the planet. Even though the mathematics behind potential vorticity can become quite complex, the physical idea remains elegantly simple. When air moves within a rotating atmosphere, its spin and structure adjust in predictable ways. These adjustments help shape the vast circulation patterns that move energy across the globe. Planetary rotation therefore transforms what would otherwise be a straightforward flow of air into something far more intricate. Instead of air moving directly from warm regions to cold ones, winds curve and form bands that circle the planet. Large waves develop in the upper atmosphere. Storm systems spin and drift along these currents. From space, the result can look almost like a giant, slow-moving tapestry of clouds and winds woven around the rotating Earth. All of this complexity arises from the simple fact that the planet beneath the atmosphere is turning. A spinning sphere covered in a thin fluid layer cannot support simple straight-line motion for long. The rotation bends those motions, guiding them into spirals, waves, and swirling systems that define the weather patterns we experience every day. And so the atmosphere continues its restless dance around a rotating world, where every movement of air carries the subtle signature of the planet's spin. If sunlight warmed every part of Earth equally, the atmosphere might remain relatively calm. Air would heat and cool uniformly, and the need for large-scale motion would be minimal, but the planet receives solar energy unevenly, with far more warmth arriving in tropical regions than near the poles. That difference in heating sets the stage for a remarkable planetary circulation system. The atmosphere constantly works to move energy away from the equator toward higher latitudes. Without this redistribution, equatorial regions would become extremely hot, while polar regions would grow far colder than they are today. Instead, large-scale winds and circulation patterns transport warmth across the globe, smoothing out the extremes. Scientists describe this global redistribution using a framework known as atmospheric circulation cells. These circulation patterns divide each hemisphere into three broad zones of motion known as the Hadley cell, the Ferrel cell, and the polar cell. Each of these circulation systems plays a distinct role in moving heat, moisture, and momentum around the planet. The Hadley cell is the largest and most energetic of the three. It occupies the region stretching roughly from the equator to about 30 degrees latitude in both hemispheres. Near the equator, solar heating is intense. Warm air rises from the surface in large columns known as convection currents. As this air rises, it expands and cools, often forming towering tropical clouds and frequent thunderstorms. These rising air currents create a region of persistent low pressure near the equator, known as the Intertropical Convergence Zone. High above the surface, the rising air begins to spread outward toward the north and south. As it travels away from the equator, the air gradually cools and becomes denser. Eventually it sinks back toward the surface around 30 degrees latitude. When this air descends, it warms and dries, producing regions of relatively clear skies and stable weather. Many of the world's major deserts lie near these latitudes, including the Sahara Desert, the Arabian Desert, and the deserts of Australia. Once the air reaches the surface again, it begins flowing back toward the equator, completing the circulation loop. These returning surface winds are known as the trade winds. Because of the Coriolis effect, the trade winds do not blow directly north or south. Instead, they curve westward as they move toward the equator, forming steady winds that sailors relied upon for centuries when crossing the oceans. This entire pattern of rising equatorial air, poleward movement aloft, descending subtropical air, and returning surface flow forms the Hadley cell. Farther from the equator lies the Ferrel cell, which occupies the mid-latitude regions between roughly 30 and 60 degrees latitude. Unlike the Hadley cell, the Ferrel cell is not driven directly by strong solar heating. Instead, it emerges as a consequence of the interactions between the neighbouring circulation systems. Surface winds in this region generally blow from the west toward the east. These winds are known as the westerlies, and they influence much of the weather experienced across North America, Europe, and much of Asia. The Ferrel cell helps transport warm air from lower latitudes toward the poles, while allowing colder polar air to move equatorward at times. This region also becomes a breeding ground for large storm systems known as extratropical cyclones. These storms form where warm and cold air masses interact, creating waves and disturbances along atmospheric boundaries. Closer to the poles lies the polar cell. In the polar regions, the sun's energy arrives at a shallow angle, and remains relatively weak throughout much of the year. Cold, dense air forms near the surface and tends to sink. This sinking air creates regions of relatively high pressure over the poles. From there, air flows outward toward lower latitudes near the surface. As it moves away from the poles, the Coriolis effect deflects the motion, producing surface winds known as the polar easterlies. Eventually, this cold air encounters warmer air moving poleward from the mid-latitudes. The boundary between these contrasting air masses becomes an active region where storms frequently develop. Together, the Hadley, Ferrel, and polar cells create a vast system of atmospheric circulation spanning the entire planet. These circulation patterns are not perfectly smooth or symmetrical. Instead, they interact with continents, mountain ranges, ocean currents, and seasonal changes in sunlight. But the overall structure remains remarkably consistent. Within this system, enormous waves also develop in the upper atmosphere. These waves were first described in detail by the meteorologist Carl Gustav Rossby, whose research revealed that large-scale atmospheric motion behaves somewhat like waves travelling through a fluid. Rossby waves form when the Coriolis effect interact with the movement of air masses across the planet. Instead of flowing smoothly from west to east, high-altitude winds begin to undulate, forming slow, moving curves that can span thousands of miles. These waves shape the path of the jet stream and strongly influence weather patterns across continents. When Rossby waves dip southward, cold polar air can spill into lower latitudes, sometimes producing dramatic winter weather events. When the waves arch northward, warm air from the subtropics can surge toward the poles. The shifting position of these waves often determines where storm systems travel and how long certain weather patterns persist. The study of these large-scale atmospheric behaviors took a major step forward in the middle of the 20th century, when scientists began using computers to simulate the atmosphere. One of the pioneers in this effort was the American scientist Norman Phillips. In the early 1950s, Phillips created one of the first successful computer models of atmospheric circulation. Using an early electronic computer, he simulated how temperature differences across the planet could produce organized patterns of winds and waves. Although his model was extremely simple by modern standards, it demonstrated something remarkable. Even when the equations describing atmospheric motion were simplified, the atmosphere naturally organized itself into patterns resembling real-world circulation systems. Jet streams formed. Waves appeared in the flow. Storm-like disturbances developed. Phillips had shown that the large-scale behavior of the atmosphere could emerge naturally from the physical laws governing fluid motion and heat transfer. Today, modern supercomputers run atmospheric models that are millions of times more powerful than Phillips' original experiment. These models simulate the movement of air, heat, moisture, and clouds across the entire planet. Yet the underlying principles remain the same. Energy enters the atmosphere near the equator through solar heating. The atmosphere then transports that energy toward higher latitudes through winds, storms, and ocean interactions. This movement of energy does not occur through a single pathway. Instead, it unfolds through a combination of circulation cells, atmospheric waves, jet streams, and countless individual weather systems that form and dissipate every day. Each storm that travels across an ocean carries warm air toward cooler regions. Each rising column of tropical convection lifts heat high into the atmosphere where winds can transport it across the globe. Together, these processes form the planetary engine of atmospheric circulation. Seen from space, This engine creates some of the most beautiful patterns on Earth. Bands of clouds stretch around the planet. Spiral storms drift across oceans. Long rivers of wind sweep through the upper atmosphere. These patterns shift constantly, yet they follow a recognizable structure shaped by sunlight, gravity, and the rotation of the Earth. Through this vast system of circulating air, the atmosphere quietly performs one of its most important tasks. It moves energy across the planet, maintaining a balance that makes Earth's climate and weather possible. One of the most powerful ingredients in Earth's weather system is something so familiar that it is easy to overlook. Water. Not simply liquid water flowing in rivers or filling the oceans, but water in all three of its atmospheric forms. Liquid droplets suspended in clouds, invisible water vapor mixed within the air, and delicate ice crystals drifting through the upper reaches of storm systems. The presence of water in the atmosphere adds a remarkable source of energy to weather processes, and the key to understanding that energy lies in something known as latent heat. Latent heat is the energy absorbed or released when a substance changes phase. When liquid water evaporates and becomes water vapor, it absorbs heat from its surroundings. This heat does not raise the temperature of the vapor itself. Instead, the energy becomes stored within the molecular structure of the vapor. In effect, the energy becomes hidden, which is why the term latent heat literally means hidden heat. Later, when water vapor condenses back into liquid droplets, that stored energy is released again as heat into the surrounding air. This simple process is extraordinarily important for the atmosphere. Every day, vast amounts of water evaporate from the surfaces of oceans, lakes, and soil. Plants also release water vapor through a process known as transpiration. Together, evaporation and transpiration supply the atmosphere with enormous quantities of water vapor. As this vapor rises through the atmosphere and eventually condenses to form clouds, the stored latent heat is released. That released heat warms the surrounding air, making it more buoyant and encouraging further upward motion. This feedback process can power some of the most energetic weather systems on Earth. Thunderstorms, for example, rely heavily on latent heat release. As warm, moist air rises within a developing storm, water vapor condenses into droplets. The released heat strengthens the rising motion, allowing the storm to grow taller and more powerful. In large tropical storms such as hurricanes, the energy released through condensation becomes the primary fuel driving the entire system. Meteorologists sometimes describe hurricanes as heat engines operating on warm ocean water. The evaporation of seawater supplies moisture to the storm, and the subsequent condensation of that moisture releases enormous amounts of energy. In fact, a single mature hurricane can release heat energy at a rate comparable to several 100 trillion watts. That is roughly equivalent to the electrical generating capacity of thousands of large power plants combined. All of that energy originates from the phase changes of water. Because water vapor carries such an important supply of hidden energy, scientists often track atmospheric energy using a quantity called moist static energy. Moist static energy combines three components of atmospheric energy into a single measurement. These components include the heat content of the air, the potential energy associated with altitude, and the latent heat stored in water vapor. In simple terms, moist static energy describes how much usable energy an air parcel contains when both temperature and moisture are considered together. Air that is warm and moist contains far more energy than air that is cool and dry. When that warm, moist air begins to rise, the energy stored in water vapor can be released through condensation, intensifying atmospheric motion. Meteorologists therefore pay close attention to the distribution of moist static energy when analyzing weather systems. Regions with high moist static energy often provide the fuel for developing storms. Another important concept used to evaluate atmospheric instability is convective available potential energy, often shortened to the term CAPE. Convective available potential energy measures how much energy is available to drive rising air parcels within the atmosphere. If the atmosphere contains a layer of warm, moist air near the surface and cooler air above, a rising parcel of air may remain warmer than its surroundings as it ascends. Because warm air is less dense, it continues rising. The greater the temperature difference between the rising parcel and the surrounding environment, the stronger the upward acceleration becomes. CAPE quantifies this potential for rising motion. When CAPE values are low, the atmosphere tends to be relatively stable and vertical motion is limited. When CAPE values are high, strong convection becomes possible. Large thunderstorms often develop in environments where CAPE values are substantial, sometimes reaching thousands of joules of energy per kilogram of air. Although the term joule may sound technical, it simply represents a unit of energy. In practical terms, high CAPE values mean the atmosphere contains the potential for vigorous upward motion. Rising air can then produce towering cumulonimbus clouds that extend several miles into the sky. The importance of atmospheric energy balance was studied by many scientists during the development of modern meteorology. Among them was the Austrian physicist Max Margulis. Working in the early 20th century, Margulis examined how energy stored in atmospheric temperature differences could be converted into motion. His research helped clarify how storms draw energy from temperature contrasts between air masses. In particular, Margulis studied how the potential energy contained in horizontal temperature gradients could be transformed into the kinetic energy of moving air. This work contributed to a deeper understanding of how weather systems grow and evolve. Water vapor plays a crucial role in amplifying many of these processes. Warm air can hold far more water vapor than cold air. As temperatures rise, the capacity of air to store moisture increases rapidly. For example, air at a temperature of 30 degrees Celsius can contain roughly twice as much water vapor as air at 20 degrees Celsius. This means warmer environments can store greater amounts of latent heat energy. When this moisture eventually condenses in clouds, the resulting release of latent heat can dramatically enhance atmospheric motion. In tropical regions where warm oceans continuously supply moisture to the atmosphere, this effect becomes especially pronounced. Deep convective storms regularly develop as warm, humid air rises and releases its stored energy. Even in mid-latitude regions, the presence of moisture can significantly influence storm development. When warm, moist air flows northward and encounters colder air masses, the resulting instability can fuel powerful storm systems capable of producing heavy rain, snow, or severe weather. Without water vapor, the atmosphere would still move and circulate. Winds would still form as pressure differences developed across the planet, but the intensity and complexity of weather systems would be dramatically reduced. Water vapor adds both energy and variability to atmospheric motion. It acts as a powerful amplifier, strengthening rising currents, fueling storms, and redistributing heat through the release of latent energy. In that sense, the invisible vapor drifting through the air around us carries far more influence than its small concentration might suggest. At any given moment, the atmosphere contains only a few % water vapor by volume, yet that small fraction plays a central role in shaping clouds, storms, and the ever-changing patterns of weather unfolding above our heads. Look up at the sky on almost any day, and you will likely see clouds drifting overhead. Sometimes they appear as delicate wisps stretched across a pale blue background. At other times they build into towering structures that seem to climb miles into the atmosphere. Despite their enormous size, clouds begin forming in an unexpectedly delicate way. At the most basic level, clouds form when water vapour in the air condenses into tiny droplets of liquid water or small crystals of ice. Condensation occurs when air cools to a temperature where it can no longer hold all of its water vapour in gaseous form. Meteorologists call this temperature the dew point. When air cools to its dew point, water molecules begin to gather together, forming microscopic droplets. If enough droplets collect in one region of the atmosphere, they scatter sunlight and become visible as a cloud. However, the story is slightly more complicated than water vapour simply clumping together. In pure, perfectly clean air, water vapour does not condense easily. Individual molecules of water require a surface upon which they can begin assembling into droplets. Without such surfaces, condensation would require extremely high humidity levels that rarely occur naturally in the atmosphere. Fortunately, the air is rarely perfectly clean. Floating throughout the atmosphere are tiny particles known as aerosols. These particles can include dust lifted from deserts, salt crystals carried upward from ocean spray, soot from fires, pollen grains from plants, and even microscopic fragments of soil or volcanic ash. Many of these particles act as cloud condensation nuclei. A cloud condensation nucleus is a microscopic particle that provides a surface upon which water vapour can condense. Once water molecules begin sticking to the surface of one of these particles, additional molecules quickly join them, allowing a droplet to grow. The droplets that form around these nuclei are extremely small. A typical cloud droplet may measure only about 10 micrometers in diameter, which is roughly 1/10 the width of a human hair. A single cloud can contain billions upon billions of these droplets, each one suspended within the rising and sinking currents of air that move through the atmosphere. The scientific explanation for how droplets form around tiny particles was developed in the early 20th century by the Swedish scientist Hilding Köhler. Köhler studied how water vapour condenses onto microscopic particles, and developed what is now known as Köhler theory. Köhler theory describes how two competing physical processes influence droplet formation. The first process involves curvature. Very small droplets have curved surfaces, and this curvature makes it harder for additional water molecules to remain attached. The more curved the surface, the more easily molecules escape back into the vapour phase. The second process involves dissolved substances within the particle itself. Many atmospheric particles contain salts or other soluble materials. When water condenses onto such particles, the dissolved substances lower the vapour pressure of the droplet. This effect encourages additional water molecules to remain attached and helps stabilize the droplet. Köhler theory combines these two influences and explains the conditions under which microscopic droplets can grow into stable cloud particles. Although the mathematics of Köhler theory can become quite complex, the central idea is elegant. Aerosol particles help clouds form by providing surfaces that make condensation easier under normal atmospheric conditions. Without these tiny particles drifting through the air, cloud formation would be far more difficult. Once droplets begin forming, rising air currents can carry them upward, where temperatures are cooler and humidity remains high. As more water vapour condenses, the droplets grow gradually larger. In colder regions of the atmosphere, droplets may freeze into ice crystals, which can later grow into snowflakes or contribute to rainfall through additional processes. While scientists study the microscopic details of cloud formation, observers of the sky have long noticed that clouds appear in many different shapes and structures. One of the earliest systematic efforts to classify clouds was made by the English pharmacist and amateur meteorologist Luke Howard. In 1803, Howard presented a paper describing a simple, yet remarkably useful system for naming clouds based on their appearance and structure. He introduced several Latin terms that remain in use today. The word cumulus refers to clouds that appear as puffy, rounded heaps rising upward like cotton towers. These clouds often form on warm days when rising air creates convective currents. The term stratus describes clouds that form broad, uniform layers covering large portions of the sky. Stratus clouds often produce overcast conditions and can lead to light precipitation or drizzle. The word cirrus refers to high-altitude clouds composed mostly of ice crystals. These clouds appear thin and wispy, often resembling delicate feathers stretched across the upper sky. Howard's classification system was simple, yet it provided a common language that meteorologists could use to describe cloud types consistently. Over time, additional categories were added, combining these root terms to describe more complex cloud forms such as cumulonimbus, altostratus, and stratocumulus. Even today, more than 2 centuries later, Luke Howard's cloud names remain the foundation of modern cloud classification. Although clouds may appear calm and peaceful when drifting slowly across the sky, their formation depends on a dynamic balance of temperature, humidity, and air motion. For a cloud to form, several conditions must typically occur at the same time. First, the air must contain sufficient water vapor. Without enough moisture, condensation cannot produce visible droplets. Second, the air must cool to its dew point temperature. This cooling often occurs when air rises and expands in the lower pressure environment of higher altitudes. Third, the atmosphere must contain aerosol particles capable of acting as condensation nuclei. When these conditions align, clouds can appear surprisingly quickly. Air rising along mountain slopes may cool and produce clouds that cling to the peaks. Warm air rising from heated ground on summer afternoons may generate towering convective clouds within a matter of hours. Large-scale atmospheric motions can also lift air over enormous regions, producing broad cloud systems that stretch across entire continents. Aerosols influence this process in subtle but important ways. Regions with higher concentrations of atmospheric particles often produce clouds with larger numbers of smaller droplets. In cleaner air environments, clouds may contain fewer droplets that grow somewhat larger. These differences can influence how clouds reflect sunlight and how easily they produce precipitation. For example, clouds with many small droplets tend to reflect sunlight more effectively, making them appear brighter when viewed from space. Clouds with fewer but larger droplets may allow rain to form more easily as droplets collide and merge. Scientists studying atmospheric aerosols therefore play an important role in understanding how clouds influence both weather and climate. Tiny particles drifting invisibly through the air can shape the appearance of clouds, the brightness of the sky, and even the distribution of rainfall across entire regions. From a distance, clouds often look soft and weightless, yet each visible cloud represents a complex interplay of microscopic droplets, rising air currents, invisible particles, and subtle shifts in temperature and humidity. What appears to be a peaceful formation floating overhead is actually a dynamic collection of billions of tiny water droplets constantly forming, evaporating and reforming within the ever-moving atmosphere. Clouds may look substantial from the ground, yet the tiny droplets that make up a typical cloud are far too small to fall as rain. A single cloud droplet usually measures only a few micrometers across. At that size, the droplet is so light that even the faintest upward air currents can keep it suspended. Gravity pulls downward, but the droplet's tiny mass allows it to drift almost weightlessly within the moving air. For rain or snow to reach the ground, those droplets must grow dramatically larger. In fact, a typical raindrop may be 100 times larger in diameter than the droplets that first formed inside a cloud. Because volume increases rapidly as diameter grows, that means a single raindrop can contain roughly 1 million original cloud droplets. The question meteorologists once puzzled over was simple, yet surprisingly challenging. How do these microscopic droplets grow large enough to fall from the sky? The answer depends on the temperature of the cloud. In warmer clouds, where temperatures remain above freezing, rainfall often develops through a process known as collision and coalescence. Within a warm cloud, droplets vary slightly in size. Some begin a little larger than others, often because they formed around larger aerosol particles or experience slightly more condensation. Larger droplets fall slightly faster than smaller ones. As they drift downward through the cloud, these faster falling droplets collide with smaller droplets along the way. When two droplets meet, they may merge into a single larger droplet. Meteorologists call this merging process coalescence. With each collision, the droplet grows larger and heavier. As its mass increases, the droplet falls faster, increasing the likelihood of additional collisions. Over time, this process can produce droplets large enough to overcome the upward air currents within the cloud. Once a droplet reaches a diameter of roughly 1 millimeter or more, gravity usually wins the struggle. The droplet begins falling steadily toward the ground as rain. In clouds that extend into colder regions of the atmosphere, a different mechanism often dominates. Many clouds contain a mixture of tiny water droplets and ice crystals when temperatures fall below freezing. Interestingly, liquid droplets can remain unfrozen even at temperatures several degrees below 0 degrees Celsius. These droplets are known as supercooled water droplets. In the 1930s, the Swedish meteorologist Tor Bergeron and the German physicist Walter Findeisen independently described a process that explains how precipitation develops in these mixed-phase clouds. Their work is now known as the Bergeron-Findeisen process. The key to this process lies in the difference between how water vapor behaves around liquid droplets and around ice crystals. Water vapor is more likely to deposit onto ice crystals than onto liquid droplets at the same temperature. As a result, when ice crystals and supercooled droplets coexist in the same cloud, water vapor tends to migrate toward the ice crystals. The ice crystals begin to grow as vapor deposits onto their surfaces. At the same time, nearby supercooled droplets slowly evaporate, supplying additional water vapor to the environment. That vapor then deposits onto the ice crystals, causing them to grow even further. Over time, the ice crystals can become large enough to fall through the cloud. As they descend, they may collect additional droplets or crystals, forming snowflakes. If temperatures remain below freezing all the way to the ground, those snowflakes reach the surface as snow. If the falling crystals pass through warmer air layers, they may melt and arrive at the ground as rain. This elegant interaction between ice and liquid water explains why many mid-latitude storms produce precipitation even when cloud temperatures remain well below freezing. Although the physics of droplet growth is fascinating, another question naturally arises. Not every cloud produces precipitation. Some clouds drift overhead for hours without releasing a single drop of rain. Meteorologists describe this difference using a concept known as precipitation efficiency. Precipitation efficiency refers to the fraction of condensed water within a cloud that actually falls to the ground as precipitation. In some clouds, especially those with weak upward air currents, droplets may grow large enough to fall easily. These clouds often produce steady rain. In other clouds, strong upward currents keep droplets suspended for long periods of time. Even if droplets grow larger, they may be carried upward again before they can fall. As a result, a cloud may contain large amounts of condensed water while producing very little rainfall. Thunderstorms provide a good example of this effect. Within powerful convective storms, rising air currents known as updrafts can exceed speeds of 100 miles per hour. These updrafts are strong enough to keep large droplets and even small hailstones suspended within the cloud. Eventually, when the storm weakens or droplets grow too large to remain suspended, precipitation may suddenly fall in intense bursts. Because precipitation plays such a crucial role in Earth's water cycle, scientists have invested considerable effort in observing and measuring rainfall across the planet. One of the most advanced programs studying global precipitation is NASA's Global Precipitation Measurement Mission. This international satellite mission was launched in 2014 as a collaboration between NASA and the Japan Aerospace Exploration Agency. The mission uses a network of satellites equipped with specialized radar and microwave sensors to observe rainfall and snowfall across the entire globe. These instruments can detect precipitation structures inside clouds, measure the intensity of storms, and track how rainfall varies across oceans, continents, and mountain ranges. The data collected by the Global Precipitation Measurement Mission helps scientists understand how water moves through the atmosphere, improves weather forecasting, and contributes to climate research. Observations from space have revealed that precipitation is far from evenly distributed across the planet. Some tropical regions receive several meters of rainfall each year, while deserts may experience only a few centimeters annually. Storm systems moving across oceans and continents often concentrate precipitation into narrow bands, producing intense rainfall in some areas while leaving nearby regions relatively dry. Precipitation also plays an important role in the development and evolution of storms. When water vapor condenses within clouds, the release of latent heat strengthens rising air currents. These strengthened currents can intensify storm systems, allowing them to grow taller and more organized. In tropical cyclones, the continuous cycle of evaporation, condensation, and rainfall forms the core engine that powers the storm. In mid-latitude systems, precipitation often develops along frontal boundaries where warm and cold air masses interact. As these storms release rain or snow, they redistribute heat, moisture, and energy throughout the atmosphere. Each falling raindrop therefore represents more than a simple drop of water. It is the final step in a complex chain of microscopic interactions, atmospheric motions, and energy exchanges unfolding high above the surface. Billions of droplets merging, freezing, melting, and falling through layers of moving air, and eventually, after a journey that may have begun as invisible vapor rising from the ocean, the droplet reaches the ground. completing a quiet but essential cycle within Earth's ever-moving atmosphere. Across much of the atmosphere, weather unfolds slowly and steadily. Large pressure systems drift across continents, jet streams curve gently around the planet, and clouds evolve over hours or even days. Yet sometimes the atmosphere behaves quite differently. Under the right conditions, energy stored in warm, moist air can be released rapidly, producing storms that grow from quiet beginnings into towering structures within a single afternoon. These storms belong to a category of weather that meteorologists study under a field known as mesoscale meteorology. The word mesoscale refers to atmospheric phenomena that occur on intermediate spatial scales. These are weather systems larger than small local breezes but smaller than the vast circulation patterns that span entire hemispheres. Mesoscale systems typically range from a few miles to several hundred miles in size. Thunderstorm, squall lines, and clusters of convective storms all fall within this category. Although they're relatively small compared with planetary circulation patterns, mesoscale storms can produce some of the most dramatic weather on Earth. The formation of a thunderstorm depends on a combination of three fundamental ingredients. Meteorologists often summarize these ingredients as instability, moisture, and lift. Instability refers to the tendency of air to rise freely once it begins moving upward. As described earlier, instability occurs when warm air near the surface is surrounded by cooler air above. In that situation, a rising parcel of air remains warmer and less dense than its surroundings, allowing it to continue rising. Moisture provides the water vapor that fuels the storm through condensation and latent heat release. Warm, humid air contains large amounts of stored energy that can be released when water vapor condenses into cloud droplets. Lift provides the initial push that begins the upward motion. Several different mechanisms can provide this lifting force. Warm air may rise along a cold front where a mass of cooler air advances beneath it. Air may be forced upward when it encounters a mountain range. Surface heating during sunny afternoons can also create rising thermals that trigger convection. When these three ingredients combine, a thunderstorm may begin to develop. At first, the process often appears modest. Warm air rises slowly, forming a small cumulus cloud. As the air continues ascending, the moisture within it condenses, releasing latent heat that strengthens the rising motion. The cloud begins to grow taller. Within a relatively short time, the cloud can develop into a towering cumulonimbus structure, reaching heights of several miles. In some powerful storms, the cloud top may extend as high as 10 or even 12 miles into the atmosphere. Inside these storms, strong upward air currents known as updrafts carry warm air rapidly toward higher altitudes. At the same time, rain and hail forming within the cloud begin to fall, creating downward currents of cooler air known as downdrafts. The interaction between these rising and sinking currents gives thunderstorms their dynamic character. Lightning flashes through the cloud as electrical charges build up between ice particles and droplets. Thunder follows as rapidly heated air expands along the lightning channel. Rain begins falling beneath the storm, sometimes gently and sometimes in intense bursts. Most thunderstorms remain relatively short-lived, often lasting less than an hour before weakening and dissipating. But under certain atmospheric conditions, storms can become far more organized. One of the most powerful types of thunderstorms is known as the supercell. A supercell thunderstorm contains a persistent rotating updraft called a mesocyclone. The term mesocyclone refers to a region of rotating air several miles wide located within the central portion of the storm. This rotation develops when strong wind shear exists in the atmosphere. Wind shear occurs when wind speed or direction changes with altitude. For example, winds near the surface might blow gently from the south, while stronger winds higher in the atmosphere blow from the west. This variation in wind creates horizontal tubes of rotating air in the lower atmosphere. When a developing thunderstorm forms in such an environment, the rising updraft can tilt these horizontal tubes into a vertical orientation. Once the rotation becomes aligned vertically, the updraft begins spinning. This rotating updraft becomes the mesocyclone. Supercell storms are capable of producing some of the most intense weather phenomena observed in the atmosphere. Large hail, damaging winds, and occasionally tornadoes can develop within these rotating systems. One of the scientists who contributed significantly to the understanding of severe storms and tornadoes was the Japanese-American meteorologist Ted Fujita. Working at the University of Chicago during the 20th century, Fujita conducted detailed investigations of tornado damage patterns. By carefully analyzing how buildings, trees, and debris were affected by tornadoes, he developed a method for estimating tornado intensity. This method became known as the Fujita scale. The Fujita scale categorized tornadoes based on the damage they produced, allowing meteorologists to compare tornado events and better understand their behavior. Fujita also made important discoveries about how winds behave within severe storms. His research revealed the existence of intense downward bursts of wind known as microbursts. Microbursts occur when rain-cooled air descends rapidly from a thunderstorm and spreads outward when it reaches the ground. These powerful downdrafts can produce sudden and dangerous wind gusts. Through careful observation and analysis, Fujita helped reveal the complex structure of severe convective storms. Thunderstorms also have an interesting ability to organize themselves into larger systems. A single storm may begin as an isolated cell, forming in response to local heating or lifting. But under favorable atmospheric conditions, multiple storms can interact with one another. Cold air spreading outward from downdrafts can trigger new storms along its leading edge. Groups of storms may merge, forming long lines known as squall lines that stretch across hundreds of miles. In some cases, clusters of thunderstorms organize into large complexes called mesoscale convective systems. These systems can persist for many hours and produce widespread rainfall across large regions. Although each storm begins as a local burst of rising air, the interactions between storms allow them to grow into organized structures capable of influencing weather across entire states or provinces. From a distance, a mature thunderstorm may appear as a single towering cloud drifting across the landscape. Yet within that cloud exists a remarkable engine of atmospheric motion. Air rising rapidly, water vapor condensing into rain and hail, downdrafts spreading cool air outward, and rotating currents organizing the storm structure. All of these processes arise from the fundamental ingredients of instability, moisture, and lift. When those ingredients align, the atmosphere transforms stored energy into motion, creating storms that reshape the sky above us. Over the warm waters of the tropics, the atmosphere sometimes produces storms of extraordinary scale and power. From space they appear as immense spirals of cloud stretching hundreds of miles across the ocean, rotating slowly around a calm central eye. These storms are known as tropical cyclones. Depending on where they form, they may be called hurricanes, typhoons, or simply cyclones, but the underlying physics remains the same. Each of these storms is a vast atmospheric engine powered by the heat stored in warm ocean water. The idea that tropical cyclones function like heat engines has become one of the most useful ways to understand their behavior. A heat engine is a system that converts heat energy into mechanical motion. Steam engines, for example, operate by heating water to produce steam, which expands and drives pistons or turbines. Tropical cyclones operate through a somewhat similar principle, although the scale is vastly larger and the working fluid is the atmosphere itself. Warm ocean water evaporates into the air above the surface, filling the lower atmosphere with moist, energy-rich air. As this air rises within the developing storm, water vapor condenses into cloud droplets. During condensation, latent heat is released into the surrounding air. This released heat warms the air column inside the storm, lowering its pressure and strengthening the upward motion of air. As air rises near the center of the storm, additional air flows inward near the surface to replace it. The inflowing air carries more moisture and heat from the ocean. As long as the storm remains over sufficiently warm water, this cycle can continue strengthening the system. Meteorologists often describe this process using the language of thermodynamics. Heat from the ocean provides the energy input. Rising air and condensation release that energy into the atmosphere, and the resulting pressure differences generate strong winds. One of the scientists who helped clarify the thermodynamic nature of tropical cyclones was Herbert Real. During the middle of the 20th century, Real conducted important research on the structure and energy sources of hurricanes. He emphasized that tropical cyclones draw their energy primarily from the release of latent heat within rising moist air. Real's work helped establish the idea that these storms are powered by the continual transfer of heat from the ocean into the atmosphere. The ocean surface acts as the fuel reservoir, supplying warm water that evaporates into the storm's circulation. Modern research has expanded on these ideas through the work of atmospheric scientist Kerry Emanuel at the Massachusetts Institute of Technology. Emanuel developed what is known as hurricane potential intensity theory. This theory describes the maximum strength a tropical cyclone can theoretically achieve under a given set of environmental conditions. The central concept behind potential intensity theory is that hurricanes behave like heat engines operating between two temperature reservoirs. The warm reservoir is the ocean surface, which supplies heat and moisture to the storm. The cold reservoir lies in the upper atmosphere, where rising air eventually releases heat to space. The greater the temperature difference between these two regions, the more energy becomes available to drive the storm's circulation. Under ideal conditions, Emanuel's theory predicts an upper limit to how strong a hurricane's winds can become. While real storms rarely reach this theoretical maximum, the theory provides valuable insight into why some storms intensify rapidly, while others remain weaker. For a tropical cyclone to form in the first place, several environmental conditions must align. First, ocean water must be sufficiently warm. In general, sea surface temperatures of about 26 degrees Celsius or warmer are needed to provide enough heat and moisture to sustain the storm. Second, the atmosphere above the ocean must be unstable enough to allow rising air currents to develop. Third, the Coriolis effect must be strong enough to initiate rotation. This requirement explains why tropical cyclones rarely form very close to the equator. Near the equator, the Coriolis effect becomes weak, making it difficult for a storm to organize into a rotating system. Fourth, the atmosphere must not contain excessive vertical wind shear. As discussed earlier, wind shear refers to changes in wind speed or direction with altitude. Strong wind shear can disrupt the vertical structure of a developing cyclone, preventing it from organizing properly. When these conditions come together, clusters of thunderstorms over warm ocean waters may begin to organize. Air flows inward toward the developing disturbance, rising near the center and forming large cloud clusters. As the system strengthens, a rotating circulation begins to emerge. Over time, the storm can develop a well-defined central region known as the eye. The eye is often surprisingly calm compared with the surrounding storm. Winds within the eye may be light, and skies can sometimes become partly clear. Surrounding the eye lies the eye wall, a ring of intense thunderstorms where the strongest winds and heaviest rainfall occur. In powerful hurricanes, the eye wall may contain wind speeds exceeding 100 miles per hour, with towering clouds extending miles into the atmosphere. Beyond the eye wall, spiral rain bands stretch outward from the storm's center. These bands consist of clusters of thunderstorms that wrap around the cyclone like curved arms. From a satellite view, the entire structure forms a striking spiral pattern, reflecting the balance between inward flowing air near the surface and outward flowing air high above the storm. Although tropical cyclones are often remembered for the destruction they can bring when they reach land, they also play an important role in Earth's climate system. These storms act as powerful agents for redistributing heat across the planet. Tropical oceans accumulate vast amounts of solar energy throughout the year. Hurricanes and typhoons help transport some of that heat away from tropical regions toward higher latitudes. As the storm circulates, it mixes warm surface waters with cooler water below and transfers heat into the atmosphere through evaporation and condensation. Even after the storm weakens, the energy it carried continues moving through the atmosphere in the form of warm air and moisture. In this way, tropical cyclones contribute to the broader circulation patterns that help balance the distribution of energy across Earth's climate system. From space, a mature hurricane appears as a massive rotating structure slowly traveling across the ocean, yet at its heart lies a delicate balance of physical processes. Warm ocean water evaporating into moist air, rising currents releasing latent heat, pressure differences accelerating winds, rotation organizing the entire system into a vast atmospheric engine. All of these processes operate together, transforming heat stored in the ocean into one of the most powerful natural phenomena found in Earth's atmosphere. Across much of the world, especially in regions that lie between the tropics and the polar circles, the weather we experience from day to day is shaped by a particular type of storm system known as an extratropical cyclone. These storms are very different from the tropical cyclones that form over warm oceans. Instead of drawing most of their energy from evaporation and latent heat, extratropical cyclones are powered primarily by temperature contrasts between different air masses. In temperate regions, warm air from lower latitudes often encounters colder air descending from the polar regions. When these contrasting air masses meet, the atmosphere becomes a place of energetic rearrangement. Warm air is less dense and tends to rise. Cold air is denser and tends to sink. The boundary between them can become unstable, producing waves in the atmospheric flow. From these waves, large rotating storm systems can develop. Extratropical cyclones may stretch hundreds or even more than 1,000 miles across. They often bring sweeping cloud systems, bands of rain or snow, and strong winds that shift direction as the storm passes. For many people living in North America, Europe, and parts of Asia, these storms are the familiar engines of everyday weather. A clear morning may give way to increasing clouds, followed by rain, gusty winds, and eventually cooler air moving in behind the system. Understanding how these storms form became a major challenge for early meteorologists. A major breakthrough came in the early 20th century through the work of the Bergen School of Meteorology in Norway. Two key figures in this effort were the Norwegian scientist Wilhelm Bjerknes and his son Jakob Bjerknes. Working in the city of Bergen during the early 1900s, they developed a conceptual framework for understanding mid-latitude storms that became known as the Norwegian cyclone model. Their work recognized that the boundaries between different air masses behave like moving fronts. A front is essentially a transition zone where air masses with different temperatures and densities meet. The Norwegian cyclone model identified three primary types of fronts that often appear within mid-latitude storm systems. The first is the warm front. A warm front forms when a mass of warmer air moves toward a region occupied by cooler air. Because warm air is less dense, it tends to slide gradually upward over the colder air ahead of it. This slow lifting motion often produces widespread cloud layers that can stretch hundreds of miles ahead of the surface front. These clouds typically begin high in the atmosphere as thin cirrus clouds, gradually thickening into altostratus and eventually nimbostratus clouds that produce steady precipitation. Rain or snow associated with warm fronts often develop slowly and can persist for many hours. The second type of boundary is the cold front. A cold front forms when a mass of colder, denser air advances into a region occupied by warmer air. Because the cold air is heavier, it tends to wedge itself beneath the warmer air, forcing the warm air to rise rapidly. This rapid lifting can produce towering cumulonimbus clouds and intense precipitation. Thunderstorms frequently form along cold fronts when the atmosphere contains sufficient moisture and instability. Compared with warm fronts, cold fronts tend to move more quickly and produce sharper weather changes. A clear sky ahead of the front may suddenly give way to dark clouds, heavy rain, gusty winds, and sometimes lightning as the front passes. After the cold front moves through, cooler and drier air usually spreads across the region. As extratropical cyclones evolve, another type of boundary may develop known as an occluded front. An occluded front forms when the faster-moving cold front catches up to the warm front ahead of it. When this happens, the warm air that once lay between the two fronts becomes lifted completely off the ground. The result is a complex structure where colder air surrounds the storm's center at the surface, while the warm air is forced upward into the atmosphere. This stage often marks the mature phase of the storm, when precipitation may wrap around the system and the storm begins to gradually weaken. The entire development of an extratropical cyclone is closely linked to a phenomenon known as baroclinic instability. Baroclinic instability occurs when strong horizontal temperature gradients exist within the atmosphere. In mid-latitude regions, large contrasts frequently appear between warm subtropical air and cold polar air. These temperature differences create regions where pressure surfaces tilt with height. When air flows through such regions, disturbances can grow as the atmosphere attempts to convert stored potential energy into motion. Small waves develop along the boundary between the air masses. These waves amplify as warm air moves poleward and cold air moves equatorward. As the disturbance grows, a rotating storm system emerges. Baroclinic instability therefore acts as a mechanism that transforms temperature contrasts into the kinetic energy of moving air. Extratropical cyclones rarely develop in isolation. Their growth is strongly influenced by the flow of air high above the surface, particularly by the jet stream. The jet stream is a narrow band of fast-moving winds located in the upper troposphere. These winds often exceed 100 miles per hour and form along regions where strong temperature contrasts exist between air masses. When an upper-level disturbance in the jet stream passes over a developing surface system, it can enhance rising motion and lower surface pressure. This process encourages the storm to intensify. Meteorologists often describe this interaction as a coupling between upper-level dynamics and surface weather systems. Air rising within the storm removes mass from the atmospheric column above the surface. As this happens, surface pressure falls, drawing in additional air from surrounding regions. This inflow strengthens the storm's circulation. As long as the storm remains aligned with supportive upper-level winds, it can continue growing and organizing. Eventually, however, the storm begins to lose its energy source. As the cold front overtakes the warm front and the warm air becomes lifted away from the surface, the sharp temperature contrasts that fueled the storm begin to weaken. Without that energy supply, the circulation gradually fades. What remains is often a broad region of clouds and lingering precipitation that slowly drifts away with the prevailing winds. From a satellite perspective, a mature extratropical cyclone often appears as a sweeping comma-shaped cloud pattern stretching across the landscape. Within that graceful curve lies a dynamic system of interacting air masses, rotating winds, rising currents, and shifting fronts. These storms may lack the perfectly symmetrical spiral of a hurricane, yet they remain one of the most important mechanisms through which the atmosphere redistributes heat across the planet. Every passing front, every shifting wind direction, and every band of rain associated with these systems reflects the atmosphere's ongoing effort to balance the temperature differences between warm and cold regions of Earth. High above the clouds, far beyond the height of most commercial aircraft, the atmosphere contains narrow bands of extraordinarily fast-moving wind. These winds form what meteorologists call the jet streams. Although they are invisible to the eye, jet streams behave like immense rivers of air flowing through the upper troposphere. They can stretch thousands of miles across entire continents, while remaining only a few hundred miles wide and a few miles thick. Within these atmospheric rivers, wind speeds often exceed 100 miles per hour, and at times they can reach well above 200 miles per hour. The existence of these powerful currents was not widely understood until the early 20th century. One of the first scientists to document them was a Japanese meteorologist named Wasaburo Oishi. In the 1920s, Oishi conducted careful observations using weather balloons launched near Mount Fuji in Japan. Each balloon carried instruments to measure wind speed and direction at different altitudes. By tracking the movement of the balloons as they rose through the atmosphere, Oishi noticed that winds at higher altitudes were moving far faster than those near the ground. He recorded consistent west-to-east winds at high altitudes with remarkable speeds. Unfortunately, Oishi published much of his research in Esperanto, an artificial international language that was not widely read by meteorologists at the time. As a result, his findings remained largely unnoticed outside Japan for many years. Later, during the 1940s, pilots flying high-altitude aircraft during wartime reported encountering powerful winds that dramatically affected their flight times. These observations helped confirm the presence of jet streams and drew wider attention to their importance. Jet streams form primarily because of strong temperature contrasts between different regions of the atmosphere. The most prominent jet streams develop along boundaries where warm air from lower latitudes meets colder air from the polar regions. These temperature differences create sharp gradients in atmospheric pressure at high altitudes. As air flows along these gradients, the Coriolis effect deflects the motion, organizing the winds into narrow, fast-moving currents. Two major jet streams exist in each hemisphere. The polar jet stream forms along the boundary between polar and mid-latitude air masses. The subtropical jet stream forms farther south, where warm tropical air meets cooler mid-latitude air. Although these jet streams can shift in position and strength throughout the year, they remain persistent features of the upper atmosphere. The jet stream rarely flows in a perfectly straight line. Instead, it undulates across the planet in large wave patterns known as Rossby waves. These waves can extend thousands of miles from north to south and play a crucial role in shaping weather patterns. When the jet stream dips southward in a Rossby wave trough, colder polar air often spills into lower latitudes. When it arches northward in a ridge, warm air from subtropical regions can surge poleward. These waves therefore help determine whether a region experiences cold outbreaks, warm spells, or prolonged periods of unsettled weather. Because mid-latitude storm systems tend to travel along the jet stream, meteorologists often describe the jet as steering the movement of storms. Low-pressure systems frequently develop beneath regions where the jet stream curves and accelerates. These regions encourage rising air motion, which helps storms intensify. As a result, the path of the jet stream often determines where storms will travel and how long they will influence a particular region. A strong jet stream may guide storms rapidly across continents, producing changing weather conditions every few days. When the jet stream becomes weaker or more stationary, weather patterns may linger in one place for extended periods. Understanding how energy moves through these atmospheric waves requires additional concepts from atmospheric dynamics. One of these concepts is known as Eliason-Palm flux. The Eliason-Palm flux describes how atmospheric waves transport momentum and energy through the atmosphere. Developed through the work of meteorologists Arndt Eliason and Eric Palm, this concept helps scientists understand how large-scale waves interact with the background flow of the atmosphere. In simple terms, atmospheric waves do not merely drift passively within the wind. They actively exchange energy and momentum with the surrounding air. Through these exchanges, waves can strengthen or weaken the jet stream, alter its path, and influence the development of storm systems. Although the mathematics of Eliason-Palm flux can become quite technical, the physical meaning is straightforward. Energy is constantly being transferred between atmospheric waves and the broader circulation of the atmosphere. This transfer helps shape the large-scale patterns of wind that dominate the upper troposphere. Because the atmosphere is a three-dimensional fluid, these upper-level motions strongly influence what happens at the surface. When air diverges in the upper atmosphere, it effectively removes mass from the air column beneath it. This removal lowers the pressure near the surface, encouraging air to flow inward and rise. Rising air often leads to cloud formation and storm development. Conversely, when air converges in the upper atmosphere, it adds mass to the air column below. Surface pressure increases and air tends to sink. Sinking air suppresses cloud formation and often produces clearer skies. In this way, the behavior of winds several miles above our heads can determine whether the weather at the surface becomes stormy or calm. Meteorologists therefore pay close attention to upper-level atmospheric patterns when forecasting weather. Satellite imagery, weather balloons, and aircraft observations provide data about the position and strength of jet streams around the globe. Numerical weather models use this information to simulate how the upper atmosphere will evolve in the coming days. By understanding how the jet stream curves, accelerates, and interacts with atmospheric waves, scientists can anticipate where storms are likely to form and how they may travel. Although these powerful winds remain invisible to anyone standing on the ground, their influence quietly shapes the weather experienced by millions of people. High above the familiar landscape of clouds and precipitation, these fast-moving rivers of air guide the movement of storms, redistribute energy across continents, and connect the circulation of the entire atmosphere into a single dynamic system. If the atmosphere were the only moving fluid on Earth, weather would still exist, but it would behave very differently. Covering more than 70% of the planet's surface are the oceans, and these vast bodies of water interact continuously with the air above them. Heat, moisture, and momentum move back and forth across the boundary between ocean and atmosphere every moment of every day. This relationship is known as ocean-atmosphere coupling. The phrase may sound technical, but the concept is quite intuitive. The ocean and the atmosphere behave as a connected system. Changes in one influence the other. The ocean absorbs enormous amounts of solar energy. Water has a much higher heat capacity than air, meaning it can store large quantities of heat without changing temperature quickly. This property allows the oceans to act as massive reservoirs of thermal energy. When winds blow across the ocean surface, they stir the upper layers of water and influence the movement of currents. In return, the ocean releases heat and water vapor back into the atmosphere through evaporation. Warm ocean surfaces provide energy and moisture that help fuel storms, while cooler waters can suppress atmospheric convection. This exchange means that ocean conditions often shape weather patterns over enormous distances. One of the most influential examples of this coupling occurs in the tropical Pacific Ocean. Under normal conditions, strong trade winds blow from east to west across the equatorial Pacific. These winds push warm surface water toward the western Pacific near Indonesia and Australia. As warm water piles up in the west, colder water rises from deeper layers in the eastern Pacific near the coast of South America. This upwelling brings nutrient-rich water to the surface and helps maintain relatively cool ocean temperatures in that region. The atmosphere responds to this pattern. Warm ocean water in the western Pacific promotes rising air and frequent thunderstorms, while the cooler eastern Pacific tends to experience more stable atmospheric conditions. In the 1960s, the Norwegian-American meteorologist Jacob Bjerknes recognized that the atmosphere and ocean were linked in a feedback system across the Pacific. Bjerknes connected two phenomena that had previously been studied separately. One was a periodic warming of ocean waters along the coast of South America known as El Niño. The other was a pattern of shifting atmospheric pressure across the Pacific known as the Southern Oscillation. By showing that these processes were connected, Bjerknes described what is now called the El Niño Southern Oscillation, often shortened to the acronym ENSO. During an El Niño event, the normal trade winds weaken. Without the strong winds pushing warm water westward, the warm surface waters begin spreading eastward across the Pacific. As the eastern Pacific warms, the pattern of rising and sinking air across the tropics shifts. Thunderstorm activity moves eastward, altering rainfall patterns across large portions of the globe. Regions that normally experience heavy rainfall may become unusually dry, while other regions may receive far more rain than usual. El Niño events often influence weather across North and South America, Asia, Africa, and even parts of Europe. In contrast, a La Niña event represents the opposite phase of this cycle. During La Niña conditions, the trade winds strengthen, pushing even more warm water toward the western Pacific. The eastern Pacific becomes cooler than average, and the atmospheric circulation intensifies. These changes can influence hurricane activity, monsoon patterns, and winter weather across many continents. Although El Niño and La Niña events typically develop over periods of several months, their effects can persist for a year or more. The ability of ocean temperatures to shape global weather demonstrates how tightly connected the ocean and atmosphere truly are. Scientists studying ocean circulation have contributed greatly to our understanding of these interactions. One influential figure in this field was the oceanographer Walter Munk. Often called the Einstein of oceanography, Munk conducted pioneering research on ocean currents, tides, and the movement of energy through the oceans. His work helped reveal how wind-driven circulation and ocean basins interact to produce large-scale patterns of ocean movement. These patterns include vast gyres, which are rotating systems of ocean currents that span entire ocean basins. The Gulf Stream in the North Atlantic and the Kuroshio Current in the Pacific are well-known examples of currents within such gyres. Ocean currents transport enormous quantities of heat around the planet. Warm water flows away from tropical regions toward higher latitudes, while colder water moves toward the equator at depth. This circulation helps moderate global climate by redistributing thermal energy. Beyond the year-to-year variability of El Niño and La Niña, the ocean also exhibits longer-term patterns of temperature change. One such pattern is known as the Pacific Decadal Oscillation. The Pacific Decadal Oscillation describes shifts in sea surface temperatures across the North Pacific Ocean that persist for decades at a time. During one phase of the oscillation, waters along the west coast of North America tend to be warmer than average, while the central North Pacific becomes cooler. During the opposite phase, this pattern reverses. Although the Pacific Decadal Oscillation operates more slowly than the El Niño Southern Oscillation, it can influence weather patterns across the Pacific Rim for many years. For example, certain phases of the oscillation are associated with increased rainfall in parts of North America, while other phases may coincide with extended drought conditions. The ocean therefore acts not only as a short-term energy source for storms, but also as a long-term regulator of climate variability. Changes in ocean temperature can influence where storms develop, how strong they become, and where rainfall patterns shift. Warm ocean waters often enhance atmospheric convection, increasing the likelihood of thunderstorms and tropical cyclones. Cooler waters can suppress these processes, stabilizing the atmosphere and reducing storm activity. Because of these effects, meteorologists carefully monitor sea surface temperatures around the world. Satellites measure ocean temperatures from space, while networks of buoys and research vessels collect detailed observations from the ocean surface and below. These measurements help scientists detect developing El Niño events, track changes in ocean circulation, and improve seasonal weather forecasts. The interaction between ocean and atmosphere is therefore not a one-way process. Winds drive ocean currents. Ocean temperatures influence atmospheric circulation. Storms mix the ocean surface and redistribute heat. Together, the ocean and atmosphere form a tightly connected system that operates across timescales ranging from days to decades. Even when the ocean appears calm and unchanging from the surface, enormous amounts of heat and motion are quietly flowing beneath. And through their constant exchange of energy, the oceans and the atmosphere work together to shape the weather patterns that unfold across the planet. Although the atmosphere often appears smooth and continuous when viewed from above, the surface of Earth is anything but uniform. Mountains rise thousands of meters into the air, valleys carve deep pathways through landscapes, coastlines divide land from ocean. All of these features shape the movement of air in subtle but important ways. When winds encounter mountains, the atmosphere must adjust. Air cannot simply pass through solid rock, so it is forced to move around or over the obstacle. When air flows toward a mountain range and begins climbing the slope, a process known as orographic lifting occurs. As the air rises along the mountainside, it expands because the surrounding pressure decreases with altitude. This expansion causes the air to cool. If the rising air contains sufficient moisture, the cooling may bring it to its dew point temperature. When that happens, water vapor condenses into cloud droplets. Clouds often form along the windward side of mountain ranges where moist air is forced upward. Continued lifting may produce precipitation in the form of rain or snow. Many mountainous regions around the world receive significant precipitation because of this process. The western slopes of the Cascade Range in the northwestern United States, for example, receive abundant rainfall as moist air from the Pacific Ocean rises over the mountains. The same principle applies in many other places. When moist air flows toward mountain ranges such as the Andes in South America or the Southern Alps of New Zealand, clouds and precipitation frequently develop on the windward slopes. But the story does not end once the air reaches the mountain crest. After crossing the summit, the air begins descending along the leeward side of the range. As the air descends, it becomes compressed by increasing pressure at lower altitudes. Compression warms the air. This warming reduces relative humidity and often causes clouds to evaporate. The descending air becomes drier as it continues downward. The result is a phenomenon known as a rain shadow. In rain shadow regions, the leeward side of a mountain range receives far less precipitation than the windward side. Because most of the moisture has already fallen as rain or snow on the windward slopes, the descending air arrives on the opposite side much drier. Many deserts around the world owe their existence to rain shadow effects. The Atacama Desert in northern Chile lies in the rain shadow of the Andes Mountains. The Sierra Nevada in California helps create the dry environment of the Great Basin in the western United States. Even relatively modest mountain ranges can influence local rainfall patterns by redirecting air currents and removing moisture through orographic precipitation. Mountains influence the atmosphere in another fascinating way as well. When stable air flows across a mountain range, it may not simply rise and descend smoothly. Instead, the airflow can begin oscillating up and down as it moves downstream from the mountains. These oscillations form atmospheric gravity waves. The term gravity wave refers to waves created when gravity attempts to restore equilibrium in a displaced fluid. A useful comparison can be made with water flowing over a submerged rock in a river. As the water moves past the obstacle, it may develop ripples that propagate downstream. In the atmosphere, similar waves can form when air flows across mountain barriers. The air rises over the mountain, then sinks and rises again in a repeating pattern of oscillations. These patterns can extend many miles downwind of the mountain range. When clouds form within the rising portions of these waves, they may appear as smooth, lens-shaped formations known as lenticular clouds. These clouds often hover over mountain ranges and may appear nearly stationary even though strong winds are passing through them. Pilots flying through mountainous regions are particularly aware of atmospheric gravity waves because they can produce areas of turbulence as well as strong updrafts and downdrafts. Scientific understanding of these wave processes has been advanced through the work of researchers studying atmospheric dynamics. Among them is Joseph Klemp, a meteorologist known for his contributions to the study of atmospheric wave dynamics and severe storm structure. Through numerical simulations and theoretical work, Klemp helped clarify how atmospheric waves interact with terrain and how airflow responds to obstacles such as mountain ranges. His research improved the understanding of how gravity waves propagate through the atmosphere and how they influence cloud formation and local weather patterns. Not all terrain-related winds involve large mountain ranges. Local landscapes can also produce daily wind patterns that arise from differences in heating and cooling between slopes and valleys. One example is the anabatic wind. During sunny days, mountain slopes warm as they absorb solar radiation. The air in contact with the heated slopes warms as well and becomes less dense. This warmer air begins to rise along the slope, producing a gentle upward flow known as an anabatic wind. These upslope winds are common during the daytime in mountainous regions. At night, the situation often reverses. After sunset, mountain slopes lose heat through radiation and begin cooling rapidly. The air in contact with the cooling ground becomes colder and denser. Because colder air is heavier, it begins flowing downhill into valleys below. This downward flowing wind is known as a katabatic wind. Katabatic winds can sometimes become surprisingly strong, especially in regions where cold air accumulates at higher elevations before descending into lower terrain. Large-scale katabatic winds occur in places such as Antarctica and Greenland, where extremely cold air flows downslope from ice-covered plateaus toward the surrounding coastlines. Even on smaller scales, katabatic winds can influence nighttime temperatures in valleys by allowing cold air to pool in low-lying areas. Through these processes, the shape of the land continually interacts with the motion of the atmosphere. Mountains lift air and trigger rainfall. Descending air creates rain shadows and dry climates. Waves ripple through the atmosphere as winds cross rugged terrain. Meanwhile, daily cycles of heating and cooling drive local winds that move gently up and down mountain slopes. Although these effects occur on regional and local scales, they illustrate an important principle. The atmosphere does not move across a perfectly smooth planet. Instead, it flows over a landscape filled with mountains, valleys, coastlines, and plateaus. Each of these features leaves its signature on the winds, clouds, and rainfall patterns that develop above them. In this way, the shape of Earth itself becomes an active participant in the creation of weather. Predicting the weather has fascinated humans for centuries. Long before satellites and computers existed, farmers, sailors, and travelers relied on careful observation of the sky. They noticed patterns in clouds, winds, and temperature changes, gradually learning to recognize signs of approaching rain or clearing skies. Those traditional methods still hold value today. Yet modern forecasting now relies on something far more powerful. Weather prediction has become a problem of physics, mathematics, and computing. The approach used today is known as numerical weather prediction. In numerical weather prediction, scientists represent the atmosphere using mathematical equations that describe how air moves, how heat flows, and how moisture behaves. These equations include the conservation of momentum, the conservation of energy, and the conservation of mass. Earlier discussions introduced the Navier-Stokes equations, which describe the motion of fluids such as air. Meteorologists combine these equations with additional relationships describing thermodynamics and radiation. The computer models used in forecasting solve these equations repeatedly across a three-dimensional grid that covers the entire planet. Each point in this grid represents a small portion of the atmosphere. The model calculates temperature, pressure, humidity, wind speed, and many other variables at each point. Once the model has an accurate description of the atmosphere of the present moment, it calculates how those conditions will evolve over time. In effect, the model steps forward into the future by solving the equations again and again. To perform these calculations, enormous quantities of observational data must first be collected. Weather stations at the surface measure temperature, pressure, and wind. Weather balloons rise through the atmosphere carrying instruments that record conditions at various altitudes. Satellites observe cloud structures, ocean temperatures, and atmospheric moisture from space. Aircraft also contribute measurements during routine flights. All of this information is combined through a process called data assimilation. The model integrates these observations into its initial description of the atmosphere before beginning its forecast calculations. Because the atmosphere is so vast and complex, even modern supercomputers must simplify certain aspects of the system. Atmospheric models divide the planet into grid boxes that may span several kilometers horizontally and hundreds of meters vertically. Within each grid box, the model calculates average conditions rather than tracking every individual cloud droplet or air molecule. Even with these simplifications, the number of calculations required is staggering. A global weather model may perform trillions of calculations to simulate only a few days of atmospheric evolution. The development of these models has benefited greatly from the work of atmospheric scientists who refine the numerical techniques used in forecasting. One such scientist is Akio Arakawa. Working at the University of California, Los Angeles during the 20th century, Arakawa made important contributions to the stability and accuracy of atmospheric models. One challenge in numerical modeling arises from representing small-scale processes such as convection and turbulence that occur at scales smaller than the grid spacing of the model. Arakawa developed methods known as parameterizations that allow models to represent the average effects of these smaller processes without resolving them directly. His work helped prevent certain types of numerical instability that could cause models to produce unrealistic atmospheric behavior. Thanks to these improvements, modern forecasting models have become far more reliable. Yet even with powerful computers and detailed observations, forecasting still faces a fundamental limitation. The atmosphere is an example of a chaotic system. This idea was famously explored by the meteorologist Edward Lorenz during the 1960s. Lorenz was studying a simplified atmospheric model using one of the early computers available at the time. During one experiment, he attempted to repeat a previous simulation by entering the same initial conditions. However, instead of typing the original numbers exactly, he entered rounded values that differed by only a tiny amount. To his surprise, the new simulation produced dramatically different results. This discovery revealed something profound about atmospheric systems. Small differences in initial conditions can grow over time, eventually leading to entirely different outcomes. Lorenz described this phenomenon using the now famous metaphor of the butterfly effect. The phrase suggests that the flap of a butterfly's wings in one part of the world might eventually influence weather patterns somewhere else. Although the metaphor is poetic, the underlying scientific principle is precise. In chaotic systems, tiny uncertainties in the starting conditions can amplify as time progresses. Because it is impossible to measure every detail of the atmosphere perfectly, some degree of uncertainty always exists in the initial data used by forecasting models. As the model simulations move forward in time, these small uncertainties grow. During the first few days of a forecast, the uncertainties remain small enough that predictions remain highly reliable. Weather forecasts for the next day or two are often quite accurate. Beyond several days, however, the uncertainties begin to spread. Forecast models may still capture the general pattern of atmospheric circulation, but the precise timing and location of weather events become more difficult to predict. To address this challenge, meteorologists often use a technique known as ensemble forecasting. Instead of running a single forecast simulation, the model is run many times with slightly different initial conditions. Each of these simulations represents a plausible version of how the atmosphere might evolve. By comparing the results of these multiple simulations, scientists can estimate the range of possible outcomes. If all simulations produce similar results, confidence in the forecast is high. If the simulations diverge widely, forecasters know that the atmosphere is entering a more uncertain state. Ensemble forecasting therefore provides a way to quantify uncertainty, rather than attempting to eliminate it. Over time, the growth of uncertainty imposes a natural limit on weather prediction. In practice, detailed forecasts beyond about 10 days become increasingly unreliable. Large-scale patterns may still be predicted weeks in advance, but the specific timing and location of storms or rainfall events become much harder to determine. This limitation is not caused by inadequate technology or insufficient computing power. It arises from the fundamental nature of the atmosphere itself. The atmosphere is an enormously complex system composed of countless interacting processes. Tiny variations in temperature, humidity, or wind can eventually alter the evolution of entire weather systems. Despite these limits, modern forecasting has achieved remarkable success. Advances in satellite observations, computer modeling, and atmospheric science have dramatically improved the accuracy of weather forecasts over the past several decades. Forecasts that once extended only a day or two into the future can now provide useful guidance for a week or more. Emergency planners can track the approach of hurricanes days in advance. Farmers can anticipate rainfall patterns that affect crops. Airlines adjust flight routes based on predicted winds and storms. Even though perfect prediction remains impossible, the science of forecasting continues to improve our understanding of the atmosphere. Each new observation, each improved model, and each refined theory helps scientists better anticipate the restless movements of the air above us. In the end, weather prediction reveals something both humbling and fascinating. The atmosphere follows the laws of physics with remarkable precision. Yet within those laws lies a sensitivity so profound that even the smallest differences can grow into entirely new patterns. And so the science of forecasting continues its careful balance between knowledge and uncertainty, exploring the ever-changing behavior of Earth's dynamic atmosphere.